an electric current due to motion or change in field. Okay? So the law that governs all of this is what we call Lenz's law. Lenz's law. And Lenz's law states that an induced magnetic field is created to oppose a change in an existing magnetic field. An induced magnetic field is created to oppose a change in an existing magnetic field. All right, so we've already seen this drawing a few times. There's my magnetic field. Here's a coil of wire inside that magnetic field. There are the armatures. And here's my voltage source. Okay, so I've got an electric motor. Using the right-hand rule for force on a charge, we can figure out which way this thing's going to spin when we turn on the electricity, correct? To do that, what do I need to do? Right-hand rule. So I'm going to point my fingers in the direction of the magnetic field. For this segment of wire, current's coming out of the positive side, moving up. This segment of wire gets pushed into the page, X's. Then it goes up and around this segment of wire, current's going down, magnetic field is still that way, so that segment gets pulled out of the page, circle with dots. What happens here? What happens here? Why? Parallel to the field, so nothing happens. And I get this to start creating motion. I've got an electric motor, right? Motor. Yeah, Will. Sure. So I've got the positive side of my battery, therefore I know current's going out this way. Current in this segment's going up. Current in that segment's going up. Magnetic field is going that way. Magnetic field is going that way. And therefore the force is being pushed down into the page. Okay? On this side, exact opposite. Magnetic field still going in the same direction. Current's now coming down, but my palm is now facing up out of the page. So it gets pushed up. And I get this thing to spin like this. Good? Okay. All right. So what we're now really looking at is that was turning current into motion. We're now going to turn motion into current. So we've still got our magnetic field here. And I've still got my loop of wire. But now rather than connecting it to a battery, I'm just going to hook it up to a voltmeter. And now I'm going to cause it to spin. I'm going to push this end down, and this end comes up. So I've got a magnetic field going that way. I've got motion going like this, exactly the same. Which direction do you anticipate current is now going to flow? You did this, correct? Okay, so in the same direction that we would have anticipated it flowing in this one, right? Okay, here's the problem. If I push down on this side comes up, I create current, okay? If it flows this way, then I get current flowing this way, it creates motion like this. I have motion, I create current in this fashion. I have current, I get motion. I have motion, I get current. And I have a runaway feedback loop, which totally violates conservation of energy. If the electrons flow in the same direction that they would have in a motor, with the same direction of spin here, then current and motion should be a positive feedback loop. And once I turn on a motor, I should be able to just take the wires, connect them, and it runs infinitely forever. That is so not how the universe works. Lenz's law indicates that it has to be created to oppose a change in the existing magnetic field. So actually, it's going to go the other way. So current's going to be created in the opposite direction. And to demonstrate this, or rather to predict this, we can use the right-hand rule for induction. And rule for induction. For this, our fingers still represent magnetic field. Our magnetic field. For this, now rather than representing direction of current, our thumb points in the direction that the wire is moved. Thumb, direction of wire motion. And lastly, our palm, now rather than being force, is electromotive force, or fancy physics talk for voltage. Palm points in direction of electromotive force. Which is totally just fancy voltage. Okay. So here, I use the right-hand rule for force on a charge. Magnetic field is following my fingers. Thumb points with the current. Palm says this side gets pushed down and this thing rotates. That's a motor. Here, my fingers point in the direction of the electric field, but now my thumb points in the direction that I push this wire. My palm now points in the direction that the current is flowing, this way. Okay, on this side, fingers are pointing in the direction of magnetic field. Thumb is pointing in the direction that the wire is being pushed or pulled. Palm is then pointing in the direction of the electromotive force or current flowing that way. Okay, to differentiate between these two rules, the first rule is used if you're creating motion. This rule is used if you're creating current. So determine what you're creating before you pick which rule you're going to use. No. Things worth noting, these things look almost exactly alike, yeah? It's just a matter of whether I put a battery or a voltmeter there. An electric motor and an electric generator are almost the exact same machine. If you think about just like a simple Lego motor, everybody played with a Lego motor at some point? Yes. Okay. You can actually create a current using those if you just spin them fast enough. You can get other things to be powered. Okay. They're literally the same machine. How they're ratioed is a little bit different for efficiency purposes, but they're the same device. Okay. All right. Next up, you guys remember there was a FET sim that I keep saying, oh, we'll finish it later. Oh, we'll finish it, but we're going to finish it now. Transformers. Yeah, you have a lot of stuff to do. All right, transformers. So a transformer is a device that steps up or steps down voltage so that it can actually be used in a device. So a device that increases or decreases voltage using magnetic fields. So really how we design a transformer starts in the same way we had those solenoids drawn earlier this week. So we've got a whole bunch of coils wrapping around some soft magnetic material. It's like one of the two things I can draw well. And we hook it up to a voltage source and we can get current, right? So I can use my second right-hand rule, the one for solenoids, so that positive current comes out here, and what wraps in the direction that current goes? I mean, what part of your hand? Your fingers wrap in the direction that current goes. Okay? Your thumb then points towards the end pole of the magnet. N, S. Rather than just wrapping it around a single bar, though, we created around a loop or something that we can wrap another portion of wire around. So in this case, I've got wire going here. And I'm going to, rather than connecting this to a power source, I'm going to connect it to a voltmeter. So I've got what we call a primary coil and a secondary coil. Okay? When I turn the current on here, I create a magnetic field. This one will then also create a magnetic field and therefore a current. We can determine which side or which direction the current will flow on this one based on Lenz's law. So because this one's creating a magnetic field going this way, how should this one's magnetic field now be created? How should this one create a magnetic field in response? Fingers down. People agree? So this coil is creating a magnetic field directed this way. How is this one going to respond? What kind of magnetic field is it going to create? Hunter's given us this direction. Do you have a reason for that direction? Because it's the same. Created to oppose. Thumb up. Okay? So this one's coil is going to respond by creating a magnetic field that opposes that change. So let's take a look at why. If this coil creates a current that creates a magnetic field, and then this one created a magnetic field that pushed in the same direction, we get that same runaway idea where we break the law of conservation of energy. So then the magnetic field would amplify the current here, which would make a stronger magnetic field, amplifying the current here, which would make a stronger magnetic field, and around and around and around it goes infinitely. That violates conservation of energy real quick. Instead, what this does is it pushes back. It decreases the magnetic field, which pushes back on the electric current, and we wind up making an electric current that forms a magnetic field in opposition to the one that already existed. So here, my thumb's going to point up, my fingers are going to wrap like this, current's going to flow this way. Okay? The reason we would actually use one of these is to show a relationship between, or sorry, not show a relationship, but to change voltage. And it depends entirely on the number of times these are wrapped around these cores. So this one's wrapped 1, 2, 3, 4, 5 times, 5 coils. This one's wrapped 1, 2, 3 times, 3 coils. And those coils form a ratio with the voltage that they're set up at. Let's say this is a 12-volt battery. We can now figure out what voltage is going to be read out over here. It's determined as the number of coils divided by the voltage. It is equal to the number of coils on the other side divided by the voltage on the other side. Okay? So if I've got 5 coils divided by 12 volts, that's going to be equal to 3 coils divided by whatever V2 is. Multiply, divide. I'm going to get 36 over 5 is equal to V2, which means that V2 is 7.2 volts. So this would be what we call a step-down transformer. The voltage has now been stepped down into the second set. This is what you see on most devices you plug into the wall outlets. Your cell phone charger, that like brick that actually sits on the wall, is a transformer. It's stepping the electric current down from 120 volts, usually like 5 to 20. So depending on the exact cell phone you're using and exactly what current it's, what voltage it wants to use to charge, it brings it way down from that 120 value. 120 value is set so high so that it can move easily throughout your house or throughout the school building, etc., without a lot of loss of energy due to heating of wires. Questions about this setup or this equation? Let's go ahead and take a look at your PET sim. Open up your PET sim. Let's say maintain conservation of energy. The amount of power of this side needs to be equal to the power output of this side. Otherwise, we'd somehow gain energy somewhere, or we'd be losing energy, which is possible due to a little bit of heating, but we can't gain energy at all. So in an ideal transformer, these are going to have equal amounts of power. I believe that's question 7 or 8. You should probably take a look. Okay, so what I can show then is that power 1 is equal to voltage 1, current 1, and power 2 is equal to voltage 2, current 2. And since we just said power 1 must equal power 2, otherwise we violate conservation of energy, we show that V1 I1 must equal V2 I2. Everybody good with that statement? Okay. In this problem, we are told that current in the secondary is 1 amp. We are told that voltage in the primary is how much? 25 volts? Is that correct? 25 volts. And we are told that the total power was 100 watts. So I can use this first power equation, 100 equals 25 times I, to find the current. What's the current going to be? Okay, so I get 4. And that's going to be equal to V2 times I2. What's V2? It's a number. How much is V2? Come on, guys. How much? It's 100. I heard it here and I heard it there about the same time. A little worried about us right now and our algebra skills. 25 volts times 4 amps is 100 divided by 1. We're good? Okay, so 100 volts is V2. All right. The question for number 10 asked what the coil turn ratio is for this hypothetical transformer. We can determine the coil turn ratio based on this equation here. We now have voltages for V1 and V2. We now know that N1 divided by V1 is N over 25, and this is N2 over 100. So what's your coil turn ratio going to be? I'm not looking for the exact number of coils that one side or the other has. I'm looking for the ratio between the two. 1 to 4. Okay. Anybody questioning how he got that? Right? Right? Yeah. And go 4 to 1 or 1 to 4? Yeah. All right. It's really the same depending on whether you're saying 1 to 2 or 2 to 1. Like in terms of N1 to N2 or N2 to N1. All right. Let's take one more look at that worksheet. So what is the coil turn ratio of the transformer if the output is 1 amp? Well, you should now know because Parker told you. And we should have been able to calculate number 9. You sure you didn't get number 9 right? What'd you get? Why are you wrong? Then how do you know you're wrong? I mean, what if you're right? Anybody not get 27? Okay. So either you're right or the whole class is wrong and I'm not doing anything to stop it. All right. Number 8, you should also have heard me say the answer to. And number 7, you should also be able to figure out because we just talked about power in a couple of situations here where if we have a higher voltage, meaning like a 100 volt scenario, something happened to the current. So is something stepped down when voltage is stepped up? You tell me. We totally looked at an example here. I mean, that's reasonable because I went from a 4 amp to a 1 amp. That was stepped down when 25 went up to 100. Power. No, just no. All right. I mean, possibly. All right. Questions about any of those FETSIM questions? If we're using direct current, nothing changes, then this only turns on the counter field that instant that this thing was turned on. That means there are two ways that I can get this transformer to actually work. What's one of those ways? Constantly flipping it on and off and on and off. So I've got continuous change. Every time I turn it on and off, this creates a magnetic field in opposition. I get current here. Good. There's the first answer. What's the better answer? Anybody know? Using alternating current. Okay. So rather than using direct current, transformers only work on alternating current. So our next topic here is alternating current. So direct current's what we've been using in literally every circuit that we've designed and worked with so far. However, your house runs on alternating current. Few reasons there. First of all, what is alternating current? It's current where the electrons are moving back and forth and back and forth and back and forth and back and forth 60 times per second in the United States power grid. So electrons cycle back and forth. And this is at 60 hertz in the US. I mean, it works. So the light bulbs that are currently illuminating this room are actually turning off 120 times per second because the electrons have to stop, turn around, go back the other way, stop, turn back, go around the other way. So they, in a single cycle, they've stopped twice. So at 60 hertz, we're looking at 120 times per second. Those light bulbs are turning off. That is too fast for our eyes to realize it. It is also too fast for the light bulb to cool down in between. But if we were to take a light sensor and measure the power output of these light bulbs, it wouldn't show a nice steady line. It'd give us a wave function where we're seeing the light bulbs turn on and off or get dim and bright 60 times per second. So the electrons are moving back and forth, which is why in a transformer, we can say that this is changing, flipping back and forth at 60 hertz. Questions about how that applies to a transformer? Okay, so reasons why we use alternating current in the United States. First of all, because Tesla was better than Edison. Second of all, because alternating current can be used at higher voltages with less loss of energy. It is more efficient, and has less heating loss than direct current. Less heating loss than direct current. Originally, Edison was installing direct current electricity in large cities. He was being contracted to lay lines that went all the way out and then all the way back to his power plants, and he could power different things. Tesla said, this is ridiculous. There's got to be a better way to do this, and then he invented a better way to do this that only uses half the electric line that DC current paths did. So it also uses half the wire necessary. Now, Edison, of course, being a stuck-up prick, tried to prove Tesla wrong and make it show that it was dangerous. But again, Edison was like, yeah, no, I'm smarter, and here's how it works. And that's what we use today. There's a whole bunch of documentaries on Tesla versus Edison, and they're sweet. And maybe we'll watch one next week. I don't know. What? Oh, did I say it the other way? Yeah, Tesla was all about alternating current. Did I say it the other way? Oh, I misspoke that. All right. Types of current? That is not just a band, it is one of the best classic rock bands of all time. And yeah, that's totally where they got their name. Like, actually. They're actually named after the types of electrical current. There is a lightning bolt in between. Yeah.